Let's solve problem 22 on the 2025 USNCO locals exam. It reads solid gallium melts at 29.8 degrees Celsius with an enthalpy of fusion of 5.59 kilojoules per mole. The heat capacity of solid gallium is 26.1 joules per mole Kelvin, and the heat capacity of liquid gallium is 28.5 joules per mole Kelvin. If equal masses of solid gallium at 20 degrees Celsius and liquid gallium at 60 degrees Celsius are mixed in a well-insulated container, what is the temperature after the mixture has attained equilibrium? So first we need to realize in this complex thermodynamics question that there are going to be three main steps. We have the solid going from 20 degrees to 29.8 degrees, its melting point. And then we have solid melting. And then we have the liquid going from 29.8 degrees to a T final, which could be whatever. And now the thing is, some of these may not happen. Maybe not even the first one will happen. It depends on how much heat the liquid gallium can supply by cooling down, because that's how the solid is going to get enough energy to even raise its temperature and also to melt. So let's see how much energy it takes for the solid to go from 20 to 29.8. And so we have Q equals MC delta T. And when you're doing a heat flow, you basically set Q equal to negative Q. And so it'll be Q solid is equal to negative Q liquid. And so what you're going to have here is you're going to have the Q of the solid is, and I didn't mention this, but since there's equal masses, we're just going to use some number n, like n moles of both. And this will simplify calculations a lot. So there are n moles of both because if they have the same mass, then they also have the same number of moles. And so we find the Q of the solid. It's equal to N times the heat capacity, which is 26.1, and final minus initial, 29.8, minus 20, equals negative N times the C, which is 28.5, times final minus initial, so TF minus 60. And so we can go ahead and cancel the n's, and then we can go ahead and solve for TF. So it's like negative 28.5 TF plus 28.5 minus 60, or not, that's not right, 28.5 times 60. And so we'll move this over, we'll subtract it, 28.5 times 60. And we need to divide this by negative 28.5. So let's plug this all into the calculator, and we'll find the final temperature of the liquid gallium. And if we get a nonsensical answer, it basically means that there wasn't enough heat to supply the liquid or the solid gallium to fully heat up. And so we get the final temperature to be 51.025. And so this is a valid answer because it's not any lower than 29.8 and it's not any higher than the initial temperature. And so now we're going to move on to the next phase, which is the solid melting. And so the solid melting, the Q of that is going to be N times delta H. And it's once again going to be equal to the negative Q liquid. And so what we have here is we have N delta H, and so N times the delta H, which is 5.59 times 1,000, because we need it in joules, equals negative Q. So we have negative N times the C again, which is 28.5, times TF, which we'll solve for, minus the temperature final from the previous one, which was 51. Let's just use 51. And once again, we can cancel the n's. And so 5.59 times 1,000 equals, or we should do like negative 28.5 TF plus 28.5 times 51. So once again, we'll subtract this. And then we'll divide this all by negative 28.5 to solve for TF. And now the problem is our TF is negative 145. And this is a nonsensical answer because it cannot go below the temperature of the other substance. That's simply not how heat flow works. And so that means there isn't even enough temperature to melt all of the solid. And so that means the final temperature at equilibrium will just be the melting point. It'll be in the process of melting. And the answer is A, 29.8 degrees Celsius.